In this lesson, we're going to be taking a look at some of the graphical ways to represent and to interpret rates of change. In the previous lesson, I emphasized the idea that rate of change is really tied to just the very simple idea of slope. We've packaged it somewhat differently, given it a new set of equations or a new set of ways to arrive at slope, but really we're still talking about slope. Now in this case, we're actually getting away from those different algebraic representations and we're going back to a more fundamental idea. For those of you who are familiar with some physics, this is going to be very familiar to you because of the relationship between, when we talk about the relationship between distance to speed to acceleration, from distance to speed, that's a rate of change. So speed is the rate of change of distance. Acceleration is the rate of change of speed or velocity. So that being the case, some of you may already be somewhat familiar with this. So let's go back first of all, let's talk about how does rate of change relate to the function itself. Well, since rate of change is a measurement of the slope of the function, we should be able to work between these two ideas. We can talk about what we know about the original function, or we can talk about what we know about the rate of change itself. In this case, the way I'm describing it, if we have a positive rate of change, so that means if we have a positive slope, well, what does that mean the function is doing? And if you think about that, if we come down here to this graph, so number one, if my rate of change is positive, and for now I'm just going to assume a constant positive value, well, that means that this slope, this value is a positive number, which means this slope must be a positive number. And we know that a positive slope goes up and to the right. So if I have a positive rate of change, I have a positive slope. If I have a positive slope, I have a positive rate of change. Now this positive slope could, in theory, I'm just going to break my own graph here, there's nothing saying that this positive slope couldn't occur with a line that's below the x-axis. So all of these y values could in theory be negative, but the overall slope could be positive. So that's the first thing you want to be careful of when you're looking at these things. Don't assume, don't come in with any sort of bias about where this positive slope occurs. I started here at 0, 0 because I thought that was convenient and made sense for this graph that I was putting together. If the rate of change, on the other hand, is negative, then that means that I have a negative slope. So you can see I've jumped from having a positive rate of change down here to a negative rate of change. Now this actually isn't very realistic. If we're in the real world, that's a pretty sudden change, but for the case of just talking about it mathematically, we can do something like that. So we can have this jump. So if I was positive, I have a positive slope. If I become negative, I have a negative slope, which means down to the right. And then finally, if my rate of change is 0, so if I have a 0 rate of change, that means I have a slope of 0. And again, same warning. A slope of 0 doesn't necessarily mean that this value is on 0. A slope of 0 just means I have a straight horizontal line somewhere. So again, don't get sucked into making a poor assumption there. So I could take this whole thing and I could rearrange it to look like this, and it would still satisfy this rate of change graph. Here you can see all of my values are negative. They could all be positive, or they could be crossing the x-axis as I've shown happening here. If you started with the function graph, you should be able to also work yourself backwards to the rate of change graph. So the order that I do these things is interchangeable, just depends on which one I have information about. And I'm going to actually show that in our examples. I'll show you working from one to the other. So let's do a few exercises related to this. So I'll start with, I have a function. So this one starts by describing f of x. So this is why I put the f of x graph here on the left. Sometimes it's also convenient. It doesn't work very well with my page layout, but sometimes it's actually convenient to stack these. So to put them vertically, And the reason why that's convenient is because it lets you line up the x values. So let's do this one horizontally, and on the next one I think I'm actually going to manipulate it. I'll move it so it's vertical, and I'll give you an idea of what I mean. Now normally we're not too concerned with scale here, so long as you mark things off and you do a reasonable job of making them look like things are about the right scale. Here I have a function increasing at a constant rate. Then the function is constant, and in this case a constant rate means it's increasing. Then constant means the function is not changing. Then decreasing at a constant rate. So this one is going to look like, and rather than freehand it, maybe I'll put in increasing at a constant rate, then it is constant, which is a horizontal line, and then decreasing at a constant rate. Now it doesn't actually matter if this line comes down here and meets, or maybe it extends below. You know what, I'm just going to go ahead and make it extend below because I want you to see it doesn't actually have to stop here. All that matters is, and now we take, again, so for my rate of change, what kind of slope do I have here? I have a positive slope, and the way I've drawn it here, this positive slope is, it's some sort of moderate number. So there is my positive slope, and I try to make this span about the same amount in the x direction. Then I have a constant. So that means, well, this is going to be a little bit awkward. I need something a little bit thicker here. That's too thick. All right, so maybe I'll freehand in this. So from here, I have a section where it's constant. And so that means I have my rate of change is equal to 0, and that's where I get this slope of 0. So here, my slope is greater than 0. This number is greater than 0. Here, my slope is equal to 0. This is equal to 0. And then here I have a slope that's less than 0. Now I've specifically drawn this. This is quite a bit steeper. So now my slope is negative, but it should be a larger negative number than this was a positive number. So I'm going to go further down here, and I'll put in my horizontal there. And it's not a bad idea if you were to show kind of dotted lines to show the jump. So this is horizontal, and then it jumps down to here, and then from here it jumps down to there. And so there's a sketch. You should be doing these things with rulers in general. And I could show this a lot more nicely if I wanted to take the time and format all of these. And the next one, okay, you know what, I've said it, so I might as well do that as well on the next one. So this next one, we're starting with rate of change, and then we want to know what effect that has on the function. Now, as I said, I'm going to actually, I was going to stack these. So to do that, I need to separate them from each other. Let's see how much of a mess I'm going to make when I do that. That's going to make something of a mess, but I can get around that. So I'll group that first one together, and I'll group the second one together. And now I'll try to line these up on top of each other. It doesn't actually matter which one you put on top. So they're lined up pretty well. Just trying to line up the y-axis on both. And so now it says the rate of change is constant and negative. So constant and negative. So the rate of change is constant and negative. So there we go. Then constant. It's got tilted. Then constant and positive. So from here, I have to go straight up into a positive. So the first thing I'm going to do, and I'm going to show you this, I want to show you this lining up. So I'm going to draw a vertical line here. Shift that line over. And this, I want to show you the value of, so I'm going to make that line just a dotted line, really thin. That's too thin. Okay, so I've got this dotted line over here, and that's just showing me where things are lining up. And so you can easily do that with a ruler. And then it says constant and negative, and then up here it's constant and positive. So I'm going to put in another line to represent constant and positive. And then once again, I'm just going to take a duplicate. I've got this nice dotted line that I'm using to line things up. So I will clone that and move that over to here. And then finally it says I have a 0, a rate of change of 0. So it's going to go along there. Now, as I mentioned before, these things are a little bit hard to see. So what I'm going to do is to make this a little bit easier, as I said I could, I'm just going to change this to a blue but thicker line. And then I'll go to this one, and I'll do the same thing there. Line style, I'm going to make it blue but thicker. And then I'll go to this one, and I'll change the line style to be blue but a bit thicker. Okay, now that I've done that, let's take a look at the graph we've got. My rate of change is negative, then my rate of change is positive, then my rate of change is 0. Now my function can start anywhere, so I can start it at the origin. Now that's a logical place to start. So you know what, I'm just going to go ahead and do that, but understand this could be starting anywhere. You might be given some initial condition to make you do it that way. So I'm going to start here, and this is where these dotted lines come in. Because I know that if I start here at the origin and I make a negative slope, that negative slope has to reach down and touch that first dotted line. That's where my negative slope is. Then I'm told I have a positive slope. Now to make this a little more interesting, I'm going to make this positive slope quite a bit higher, and I'm going to make this negative a little bit, so I'm going to make it a little bit more shallow. Okay, so that's a pretty modest negative slope. But now my positive slope is quite high and positive, so I'm going to use that as my excuse to go way up here. So that's quite a bit steeper than this original one. And then my slope is 0, and that means I have a horizontal line to finish things off. And this is where the idea of stacking comes in handy. You don't even need these lines to do the stacking this way. What you could do is just use your ruler and stack it this way and then line things up. So you might also choose to just use these dotted lines, for example, to join up the discontinuity in your graphs up here. And so then you end up with something that looks a little cleaner. Obviously, I have the advantage of technology for this, but you might decide that this is how you're going to draw out your rate of change, and then this, you're just going to line these up using a ruler. For example, I think I've got a ruler available. So you might just decide to, let's see if I can rotate this easily. Doesn't look like I can rotate this easily, so I'm not going to. So this is the advantage of being in the real world. You don't have to deal with things like this. Okay, so let's get rid of that. So there we go. Knowing this rate of change gave me this graph. Now you have different variations depending on what values you choose for your rate of change there. Rate of change is increasingly positive. Now this is an interesting one. I'm actually not going to be able to use the ruler for this. It's not just saying that the rate of change is positive. Actually, I can use a ruler to start. I'll just freehand this one in. The rate of change is increasingly positive. So if the rate of change was just positive and constant, that would be a horizontal line like this. But this one is saying that my rate of change is increasingly positive. Then my rate of change, I'm just going to put a dot there to indicate that I'm switching to a different mode. My rate of change is then constant. And then decreasingly positive. So it's still positive, but it's turning into a smaller number. So that would be something like that. And again, I never made it down to 0. That's fine. Now this is interesting because unlike the previous rates of change that we were looking at where it was jumping around, this is a little bit more realistic in the sense that it actually increased and decreased. Again, just like before, I could have started this at 0. I couldn't start it below 0 because it said it was always positive. So this one is always positive. So what does this mean for the function? Well, first of all, this thing has a positive slope, which means that my function here is going to have a positive slope as well. This is actually very difficult to draw, and I'm going to explain why. In this case, my slope is positive, so I'm going to go ahead and start this here at 0, 0. And if my slope is positive, that means that, well, here is my function having a positive slope. But it's saying that my function is increasing, which means the slope doesn't stay like this. The slope increases, increases, increases. But it doesn't increase in steps like this. It actually increases smoothly. So this straight line over here results in a nice smooth increase over here. So I'm going to, now if I thought that way, I might do something like this. That's an increasing slope all the time. This one now says the slope stays constant, but this is already now a pretty steep slope. So now I just carry on that line in a straight line, and then I get to here, and the slope is still increasing, but it's slowing down. So the slope is still, the slope is still positive, but the slope is decreasing. So it's not going to stay this steep, but it's still going to stay positive. So now it kind of rolls over this way. Doesn't quite reach 0. Now what I was trying to warn you about is if you make your graph too steep here, so if you end up drawing something that goes, almost vertical, you're going to end up in trouble. So you do need to at least be somewhat careful here to make sure that the graph is something that you can maintain, something you can actually draw and have it make sense. So here is where the slope is increasing. Here's where the slope was constant, and here's where the slope is positive. So how would I describe that? Let's go ahead and put a description in here. I'm going to put a 1 here, 2 here, and a 3 here for the 3 different intervals. So here, my slope is positive and my slope is increasing. That's a typical symbol we use for that. Here is 2. My slope is positive and constant. And of course a constant slope is a straight line. And then here is section 3. My slope is still positive, but my slope is decreasing. And you can see if we imagine the slope, if I drew tangent lines here, that second tangent line is not as steep as that first tangent line. This can be a difficult thing the first time you're dealing with it. And for people who've got some experience with physics, you do this quite a bit with distance and speed and acceleration, so they're probably more comfortable, more familiar with it. But in principle, so long as you're careful and think about what these things mean, remember, these rate of change graphs just represent a slope. How is this function changing? Okay, one last example, a little bit more realistic, which is we've got water flowing at a constant rate. So imagine you take a tap and you turn it on to a set rate and you leave it. So you're not going to change the flow of the water again. But we're going to fill 3 different objects which can hold this water. We're going to fill a beaker, we're going to fill a cylinder, and we're going to fill a flask. And here I've drawn an Erlenmeyer flask. This is also Beaker, but this is Beaker from the Muppet Show, and I couldn't resist putting him in. Draw a rate of change in water level. So we want to, specifically, we're looking at rate of change. So what is the rate of change in water level as time progresses for each container? So let's take a look at this first one. Let's just look at all 3 of them at first and kind of figure this out. So what's going to happen in the beaker? The beaker is pretty much a regular shape. So the rate of water going in these first 50 milliliters will be the same as the next 50, will be the same as the next 50. And then you could argue, because there's this little pouring lip at the top, at the very end it's a little bit bigger around, so the rate that the level changes, right, because we're looking at the water level, so the level is going to be increasing at a constant rate, a constant rate, a constant rate, and then it's going to increase maybe at a slightly lower rate. In the cylinder, the water level is going to increase at a constant rate. But look at the first 50 milliliters. The first 50 milliliters only goes to this height in the beaker, but it goes much higher in the cylinder because the cylinder has a smaller radius. So this one's going to be increasing at a constant rate, but the rate will be faster than the beaker because it's narrower. So the height itself will be increasing faster. And so it'll be constant, 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 constant. And then when we get to the top, again, you could make that argument about this lip. It's going to decrease by a little bit. Now the flask is by far the most interesting of the three, which is it starts off wide. So it's wider even than the beaker. So it's going to start filling slower. So it's going to be filling, but it's not going to fill at a constant rate, because as it fills, it's actually going to speed up the rate that it's filling because it's getting narrower. So the height will increase more quickly until it gets to this very narrow part at the top, which is even narrower than the cylinder. And then it'll level out because now the walls are now the same distance apart, and it will be going quite quick. So let's go ahead and try to apply some common sense to what we just said there. So in the case of the beaker, we said that the beaker will fill at a constant rate, and I'm going to put this one right in the middle. So the beaker is going to fill at a constant rate, and then at the end, because it widens, the beaker is going to fill a little bit more slowly. So that's the lip. Okay? And so let's go with that description. That's the rate of change in the beaker. And of course, it's going to drop off. This is basically when the beaker is full. Then it starts spilling all over the place, and who knows what's happening. The cylinder is going to, the rate of change in the height of the cylinder is going to be faster than the beaker because it's narrower, so it's going to be up here. And at the end there, it's just going to drop off just like the beaker did. The flask, on the other hand, is going to, the rate of change is going to be positive, but as the flask narrows, eventually the flask gets as narrow at the top as the cylinder, maybe even narrower. So the rate of change actually starts off quite low, and it increases the whole time until it reaches the very top, and then it levels out. And it doesn't have a lip at the top, so there's no fall off here when it gets wider. Oh, I shouldn't have drawn that. Hold on a second. All right, so what if this one is increasing, it's positive all the time, that means that and we're going to start this at 0 because it starts off, it's not full at all. That means that this has a positive slope the whole time, straight line, and then it slows down, so this straight line starts to level off. Doesn't show that particularly well, so I'll just put a bit of a curve there to show. That's still not showing it very well. Let me see if I put in I'll use my straight line tool for this. So this one is going to do something like that. I'm going to put a kind of a medium height because I know that the cylinder will be taller than this. And then here at the end, it's going to turn to the side. That's it leveling off, or slowing down at least. It won't necessarily level, but it will slow down. I don't think I'm going to be able to really represent that very well. This one is going to fill more quickly, so the height is going to go up faster in the cylinder, and then when it gets to that little lip, this is just going to be a little less steep. Still going to be positive, but it's going to be a little less steep. And then finally here, the height on the flask is going to start at 0. It's going to actually fill quite slowly, but then it's going to fill more quickly. So it's going to fill like this, and then what will happen? So it's going to fill this way, and then it becomes constant, which means this turns into a straight line. And again, I feel like I butchered that. Let's try that again. I'm going to make it shallower. This shape, as it turns out, is a parabola. Okay, and let's say we get to there, and then from there I will use the straight line tool to say from there it just maintains a straight line slope. So here the slope is increasing, here the slope is constant. Okay, slope is increasing, slope is constant. So I hope that's been helpful. This could be a very new, very different way of thinking about things for some people. For a lot of you, I would expect. So practice. You got some. The questions directly related to the graphs are here, and these other questions, these are just some extra problems that are related to rate of change. So extra problems on rate of change. They're not necessarily graphical rate of change. I thought I would add them in here because these are actually quite light as far as number of problems go. I tried to pick out the ones that I thought were the best, and the same thing was true from these extra problems. Okay, good luck with that.